Hello and welcome back to Zig's Math Lessons. As we begin Chapter 2 about derivatives, let's start with the derivative function. Recall that the slope of a curve, this cubic, varies as x varies. The slope of the curve being the slope of the tangent, and we can see that as x varies over the x values of this cubic function, the slope of the tangent also varies. And so the slope of the tangent is actually a function of x, and that function is called the derivative function. The derivative function. As x varies along a function f of x, the slope of the tangent also varies. Therefore, the slope of the tangent to f of x is itself a function of x. This function is called the derivative function, and its y value is the slope of the tangent to the curve, or the instantaneous rate of change at x. Here are some notations that have been developed over the years to represent the derivative function. We could say f prime of x. This was Lagrange who came up with this. There's y prime. There's dy by dx, which is Leibniz notation, very popular. D f of x by dx, and f of x could be any function of x. So we could say d sine x by dx. We could say dx squared by dx. And this one, f prime of a is equal to dy by dx at the point where x equals a. Different notations all mean the same thing. The derivative of a function y equals f of x at the point x f of x is, and here's our formula for the derivative from first principles. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Note the derivative gives the slope of the tangent for a given x value, as well as the instantaneous rate of change of y with respect to x at that x value. Example, find the slope of the tangent to the parabola when x equals 3 by differentiating using first principles. It's called first principles when you use limits to differentiate, and the process of differentiating means finding the derivative. That's all differentiating means. And so when you use limits to find the derivative, it's called first principles. And by the way, there's many other ways too that we'll get to. So let's start with first principles. Our formula, this is our first principles formula. And f of x plus h means sub in x plus h to each of those x values minus f of x. So let's plug into the formula by subbing in x plus h into each. Subtract. Now notice how it says subtract f of x. This says subtract, and we need square brackets because we're going to subtract all of f of x. So we'll subtract everything. And squaring a binomial, x squared, double the product, h squared. Distribute the 2, 2x plus 2h. Subtract 1, and distribute the subtraction. Add 3x squared, take away 2x, add 1 when you distribute the subtraction. And it appears we have some canceling or offsetting to take care of here. These two offset. This pair offsets. And on the next line, we'll distribute in negative 3x squared minus 6xh minus 3h squared plus 2h plus 3x squared. We've got some more offsetting happening. Common factor out the h, and then cancel the h and take the limit. Take the limit means sub in 0 for h, because it says the limit as h approaches 0, so this will become vapor. And we have minus 2x, we have minus 6x plus 2. So we can say f prime of x is equal to minus 6x plus 2. And so we can get the slope at any spot along that curve. If you like the slope when x equals 3, simply sub in 3 here for x. F prime of 3 is minus 16. So the slope when x equals 3 is minus 16. Let's go again. This is an example we did previously in the last unit. Find the slope of the tangent to the curve y equals root x at the point where x equals 16 by differentiating this time and using first principles. Solution, state the formula and sub in. Of course, f of x plus h is root x plus h minus f of x. That's root x. And of course, we'll rationalize, which means a difference of squares in the numerator. The x is offset, leaving h. Cancel the h's. And now take the limit, sub in 0 for h. And so we have 2 root x as a denominator. So the derivative, f prime of x, of y equals root x, is 1 over 2 root x. And so, when x equals 16, the square root of 16 is 4, and 2 times 4 is 8. And it's that simple. The slope is 1/8 when x equals 16. Let's go again, find the derivative of a function. This is a rational function. Solution, sub into the first principles formula, and I'm throwing a little bit of Leibniz notation into the mix here because it's so popular, you might as well get used to it. And x plus h is going in here and here, while minus f of x is simply subtract and copy. And now subtracting fractions, a necessary skill. Common denominator, subtract the fractions, examine it, and learn how to do it. Now into the rough area with us. Consider a over 2 over h. That's the same as a over 2 over h over 1. And when you divide by this h over 1, we're actually going to multiply by 1 over h. And when you multiply top times top over bottom times bottom, that's what you get. And the moral of the story is this. I just took the ends and put them together. A over 2 over h is a over 2h. Take a look at the ends. A over 2 over h is a over 2h. And what this tells us is, in this setup, the h joins up in here as a factor. And so here we have that setup right here, and so the h joins right up in there as a factor, like this. And meanwhile, I multiplied out the numerator, 2x squared plus 2xh, and I multiplied these out as well. 2x squared negative plus 2xh negative minus 6x negative that, so that's plus 6x, and minus 6h negative that, so that's plus 6h. We've got some offsetting. These offset. Plus 2x squared minus 2x squared. You always get a lot of this. These offset. Plus 2xh minus 2xh. These offset. Minus 6x plus 6x. Leaving behind just 6h. Tidying it up. Canceling off the h's. Taking the limit. Subbing in 0 for h. And we get 6 over x squared. And so the derivative of this, by first principles, which is these limit questions, is dy by dx equals 6 over x squared. The topic of differentiability. A function is differentiable when we can find the derivative of it. So a function is differentiable at a point x equals a if we could find the derivative at x equals a. And there's just a few details to know about this topic. The domain of the derivative is a subset of the domain of the function. So in other words, if x is in the domain of the derivative, it's certainly in the domain of the function. A function is not differentiable. In other words, basically the domain of the f prime of x is the same as the domain of f of x, except for when it's not differentiable. So it's not differentiable at x equals a if 1. The derivative doesn't exist, or f of a doesn't exist. 2. There is a discontinuity at x equals a, like a point or a jump or an infinite discontinuity. 3. If the tangent is vertical at x equals a. Now, where have you ever seen a vertical tangent before? Well, there's one. The tangent is vertical at x equals 2, and so it's not differentiable there because the slope is undefined for a vertical line. And finally, if there is a cusp at x equals a, what's a cusp? Well, these are cusps. Cusps are kinks in graphs. They're usually found when the graph changes because it's a piecewise function and will follow one piece for a while and then we get on a different piece. That's where you'll often find cusps, although not the only place. So a function will be differentiable over the entire domain of f of x except for those points where it's not differentiable, and here's 4 places where it's not differentiable. And finally, given a graph of a function, here's a cubic function, y equals f of x, it's a cubic function. Sketch the derivative of this. So I've made a parallel grid here. Here's a grid where this is unit 1, 2, 3, and so is this 1, 2, 3. They're all lined up. And so on this second grid, our task is to graph the derivative of this function, this cubic. Now you must think. The tangent is horizontal at this local maximum place. The tangent is horizontal. Therefore, the slope of the tangent is 0 right here. So there must be a 0 here if the tangent is horizontal. Here's another place where the tangent line going across this function at this minimum would be a slope of 0 because it's horizontal. The tangent would be horizontal there, and so right here we must have 0. A y value of 0 on the graph of the derivative, because the derivative is the slope of the tangent, and the slope of the tangent here is 0. The slope of the tangent here is 0. The derivative is the slopes of the tangents. And so we must have zeros there and there to go with the minimum and the maximum. Now let's consider what happens in between this maximum and this minimum, between these two red dots. This curve slopes clearly downwards. It goes down, down, down. So its slope is negative. So between these two dots, we must be underneath the x-axis. And from this point forward, it slopes up. So from this point forward, we must be above the x-axis. And all the way up to this point, it was sloping up, sloping up, sloping up. So all the way up to this red dot, we must be above the x-axis, because remember, the y value of the derivative is the slope of the function. So this is the derivative function. I'm not Zigglevia Bijstoom, but thanks for watching. If you liked it, leave a like. If you like the content, then please subscribe. And asking questions in the comments section would probably be productive.